Esse vai no inglês, cara.
Hello. Elisha that me con sharp. Japa. Japa. Oh, I did, our group. I'm telling you that our group is something. Fireboy.
That's how they do.
Oh, smoky bro.
Fireboy.
We died.
I'll change my name.
Yeah, wait oh.
No, now, see now.
I've blocked them.
Alright.
I'm enjoying this.
Why you the audio fan? Why you the?
Bọ́ọ̀lù máa padà.
Hello.
I've already unmixed myself.
Look yourself, Joe.
No.
Hey, are you
Jack,
there?
good afternoon, good evening.
Fireboy DM.
Hello.
Mute yourself, Joe. All of you should mute yourself.
Hello.
And all of you should mute yourself. Oh. Mute yourself. Mute yourself.
I beg, waiting they make una they shout now. Waiting the apple.
Ask my man God.
Now we laugh.
Bro.
That was good,
Bro.
Exactly.
Sylvester, small. Sylvester, small. Sylvester. Ọmọ tí kò lè ẹjọ́ ẹ̀rù. Olóṣì ni gbogbo yín. Kí lè wákàtí ló kíláàsì yẹn?
Ẹgbẹ́nu oṣù ẹ sọ̀rọ̀, ẹgbẹ́nu oṣù yín sọ̀rọ̀.
Bẹ́ẹ̀ni oṣù tẹ náà lọ. Bẹ́ẹ̀ni oṣù yẹn lọ.
Ẹ jẹ́ ká gbádùn.
Òde lẹ́yìn ní má lè ṣe access ní báyìí.
Ẹ ra dátà ẹ jẹ́ ká gbádùn.
I am Shama.
Òde ló wà mí.
Mute our mic. Can we mute our mic?
Welcome to my YouTube channel.
Access.
Can we mute our mic? Ẹ jẹ̀jà owó ra dátà ń ṣe ká gbádùn. Ẹ wọ ẹsẹ̀ gbé gbogbo rẹ̀ lọ́jọ́.
Say something.
Olúwa ti tó mute your mic.
Which time mute your mic? Na my phone. Which time mute your mic?
Guys, shout where you create. They shout.
Na my phone. Which time mute your mouth?
Now mute your mic, not mute your mouth.
Wow. Put your mic, you. Mute your mic.
The cause commotion. Good afternoon.
Continue. Let's be guided, please. Let's be guided, where?
When is lecturer due?
Lecturer,
You
sir,
guys
never
stop
come.
making noise now. What is wrong with you guys? No, I'm not talking to you.
I go beat lecturer house. But now my phone.
Now your phone, we're in any
And so what? Okay, I keep short, Joe. You guys did this stuff. And so what?
Guys,
and
she
so
may
on.
get it. She may get it.
Now.
No, you phone. No, you make the money. But me no dey use time bio. Me o kin dey say time. Me tell me o. Yeah.
Hello, good evening, class.
Good evening, sir.
Yes, sir.
Good evening. Hope you've been enjoying CHE 156. Very briefly, we will need to continue from where we stopped in the course. You have already been introduced to the definition of acids according to what we have in the course content. You have been introduced to the strength of acids acid and base dissociation constants. And also, we have treated some aspect of pH concepts. We have treated some aspect of this pH concept. We've looked at how you can calculate the pH of strong acid, strong base, weak acid, and weak base in solution. So today we'll continue from where we stopped, and we'll look at the question together, see how we can handle that question. After that, we'll go to the unit 6 of this course. Okay. All right. This is where we stopped in the last class. And that was when we were talking about the pH of an aqueous solution of a weak base. And I gave you this equation. I gave you this equation 12. pH equals to pKw minus half pKb plus 1/2 log C. And I told you that pKw equals to 14. We derived how we got that 14 together. And you were also informed that pKb is equal to minus log to base 10 of K subscript B. This C is the concentration of that your weak base. So let us look at this example together. The pH of an aqueous solution of a weak base. You will have to determine the pH of a 0.05 molar aqueous hydroxylamine solution, and Kb was given to be 1.1 times 10 to the power minus 8 at 298 Kelvin. How are you going to solve a question like this? First, you write the equation for this reaction. That is the hydrolysis of this hydroxylamine, which will give you this positive ion and this hydroxide ion. Then you write the formula, the appropriate formula, that is question 12, to solve this particular type of question. Your pKw is 14. You're already familiar with that. And you put the value for Kb, you enter the value for Kb into where we have minus half log, into where we have minus half into pKb. And you know that your pKb, from what we have just said, is minus log to base 10 of K subscript B. Remember, this is K subscript B, okay? You were given this K subscript B as 1.1 times 10 to the power minus 8. So you put that into this expression, and then you press your calculator very well. You also put the concentration you've been given, which is 0.05 molar, into this expression, equation 12. If you do that and you press the calculator, you should be able to get the correct answer. I know that some of you will have been following it from your side by putting your pen on paper to see what you get when you calculate, when you solve this question. Then we can go to the unit 6. The unit 6 of this course. This lecture note is already available on the LMS page. You can download it. Also, for those who get logged out, you can go to the LMS page and follow this course on YouTube. The YouTube link is already available on the LMS page, so you can watch this class live from your LMS page, or you can go to the YouTube by clicking the link on the LMS page or on your Moodle app and follow this class. Unit 6 of this course is about hydrolysis. That is the hydrolysis of salt of weak acid, weak base, strong acid, and strong base. When you put these together, how can this type of salt be hydrolyzed? That is what we're going to discuss. And at the end of this unit, you'll be able to define what a salt is and describe how a salt can be hydrolyzed. can describe it properly. So what is a salt? That is an ionic compound in which the hydrogen ion or maybe the hydroxide ion has been totally or partially replaced by a metal ion or maybe a positive radical. And from the knowledge of your secondary school days chemistry, you are familiar with the types of salts, like the normal salt, the acid salt, the basic salt, complex salt, double salt, and all those types of salt that you're familiar with. And some examples of them for normal salts, that is, you can have that when a strong acid reacts, maybe a strong acid, maybe HCl, reacts with a strong base, let's say sodium hydroxide. This can give you a normal salt like sodium chloride. That is the one you normally use as table salt at home. So you can have sodium chloride as one of the examples of this. You can have potassium chloride and so on as an example under normal salt. For acid salts, in acid salts, it can be in different ways, but when it is hydrolyzed, you will possibly get an acidic solution. And it can be formed when a strong acid reacts with a weak base, or when part of the replaceable hydrogen ion has not been completely substituted by a metal ion or maybe an ammonium ion. We can have an acid salt in that way. And an example of that is this ammonium chloride. You may likely form this by reacting ammonia with HCl, then you can have this ammonium chloride. Ammonia is a weak base. Hydrochloric acid is a strong acid. Hydrochloric acid is a strong acid. And when they come together, you can have this type of salt. They can have basic salt also, complex salts, and double salt. Examples are placed on the slide. So let us look at salt of strong acid and strong base. When the salt of a strong acid and a strong base is hydrolyzed, what is that supposed to give you? Strong acids and strong bases don't hydrolyze just like that in solution. For instance, if we use Ma to represent the salt of a strong acid and a strong base, Na, let's just call it, maybe the M is K, the A is I, or maybe the A is Cl. If you have this, we can have K plus Cl minus. K plus Cl minus. Examples of that have been placed. They have been put here on the slides, like NaCl, NaNO3, K2, SO4. If you have the salt of a strong acid and weak base, that will hydrolyze in solution to give you acidic solution. Before I move on, let me reiterate it that for the salt of a strong acid and a strong base, the salt you will form will be neutral and the pH will be 7. So the pH will be equal to 7. For instance, for NaCl, the pH, if it is very pure, the pH is 7. Okay. So when you have this second case, salt of strong acid and weak base, salt of strong acid and weak base, when that hydrolyzes in solution, it produces acidic solution. And the reason is not far-fetched. Let's take for instance, if you have a strong acid, you have a weak base, okay, then you form a salt of that is NH4Cl, and then you hydrolyze this in solution. What will you have? You will have the starting material. You will have this aqueous ammonia, maybe NH3 in solution. You have the chloride ion floating when this gets hydrolyzed in water. So you have this back, okay? Then you have this HCl, which is a strong acid. A strong acid ionizes better in solution than a weak acid. So this strong acid is going to release completely its hydrogen ion in solution. It's going to release completely its hydrogen ion in solution. And this NH3 is just a weak base. It's not going to behave as much as that of this strong acid. So the resulting solution will be acidic, and the pH on hydrolysis will be less than 7. Examples of salts like this are NH4NO3, NH4NO3, CuSO4, that's copper 2 tetrasulfate 6, and ammonium chloride. We have other examples also under that. Then the salt of a weak acid and a strong base. When this type of salt is hydrolyzed in solution, it produces, just like what you have thought in your mind, it produces a basic solution, an alkaline solution. And the pH on hydrolysis should be greater than 7. The pH will be greater than 7. Examples of that is this potassium ethanoate and maybe sodium methanoate. We have other examples of that. And how do you arrive at that? On hydrolysis, let's take, for instance, this CH3 COOK. On hydrolysis, those will give us CH3 COO minus plus K plus. Put water into this reaction, then you have CH3COOH KOH. KOH is a strong base. CH3COH, that is acetic acid, or you can call it ethanoic acid. That is a weak acid. It's an organic acid. It's a weak acid. And this potassium hydroxide is a strong base. When this is hydrolyzed in solution, when you have this KOH and this acetic acid in solution, then the resulting solution will be basic and the pH will be greater than 7. Let's move on. The third case where we have sort of weak acid and weak base. The hydrolysis of this type of salt depends on to which extent each ion you have in solution is hydrolyzed. So you can have a resulting acidic solution, you can have a resulting neutral solution, or maybe a basic solution. It depends on the type of acid and the base you put together to form this sort of weak acid and weak base. Examples of that are ammonium ethanoate. Ammonium ethanoate, that's COONH4. You can also have this ammonium ethanoate, ammonium triazocarbonate 4. These are sorts of weak acid and weak bases. Later on, we may have to make references to this type of salt when we move on. So far, we have got to the unit 7 and 8 of this class, and we are by and by getting to the end of the class. We're getting to the end of the class. Okay. And under this unit 7 and 8, we'll be looking at a buffer solution. We'll be looking at how we can define a buffer solution and buffer action, or maybe buffer capacity. Then how can we prepare a buffer? What are the uses of buffer solution? And how can we calculate the pH of buffer solutions? We'll be looking at all these concepts. We can be looking at them hand in hand. We can be considering the preparation and the uses together. We can be comparing the definition and also the buffer action together. So as we're moving on in this course, just try and follow. If you have a pen, you have a paper, just put something down, write. That will help you as we move on in this course. At the end of this unit, you are expected to be able to define what a buffer is, explain how you can prepare a buffer solution, and also determine the pH of a buffer solution. And under this determination of pH of a buffer solution, we're going to do some calculations there. And I'll also give you, maybe later, I'll give you some exercises to try on your own. So what is a buffer? A buffer is a solution which can resist a sharp change, a drastic change in pH when little amount of maybe acid or little amount of base is added to that solution, that is a buffer solution. It can resist the sharp change in pH. Let's take, for instance, well, we are not considering buffer now, but let me just use this one as an example for you. Let's say you have maybe a cylinder or maybe a beaker or so, and it's a 1 liter cylinder, a 1 liter beaker. You fill it with water up to the 1 liter mark, and then you put just 1 cm cube of HCl into this solution. The moment you put just 1 cm cube, very small, that is like 10 raised to power minus 3 dm cube. That's like 1/1000 liter. Just put 1 cm cube of HCl into this solution. The pH will change. The pH of water, just water without anything, without any impurity, the pH is 7. But the moment you just add very small amount of acid, a strong acid into this water environment, the pH can be drastically reduced. You can even have a pH of maybe 4, 5, and that is a drastic change in pH. But for buffer solutions, that does not happen. If you have a buffer solution and you add very small amount of an acid or maybe very small amount of a base into that buffer solution, the pH can change, but not very drastically. The pH will just change very slightly. So far, you have only added very little quantity of acid or base into that solution. Living systems, living organisms, every living organism has its own buffer inside it. For instance, in human being, in the human blood, the pH of human blood is 7.4. And how does the blood resist a sharp change in pH? The blood is loaded, the blood plasma precisely, is loaded with a lot of ions, a lot of buffer to resist sharp change in pH. Because if the pH of human blood is drastically changed, it can lead to a lot of complications and even, if possible, death. So naturally, the human blood has its own buffer. Nobody put it there, but naturally it's just there. Okay? There are also enzymes in human bodies who operate at specific pH. And this pH, if that pH changes drastically, there will be a problem. But in the medium where those enzymes are, there are natural buffers there that resist a sudden change in their pH. We also have buffer activity in our tears, the fluid that comes out from your eyes. Maybe when you just wake up or when you are not feeling very happy. Inside that tears, there are also lots of buffer actions there. So tear also has high buffer capacity. And other applications of that is citric acid, which is used to stabilize milk of magnesia. That's another way of making a buffer solution. Okay. All right. So buffer action. How do we make a buffer, or what do we mean by buffer action? How does a buffer act? A buffer can contain a weak acid A buffer can contain a weak acid and its salt. Not just its salt. It should be a weak acid and the salt that can be highly ionized. That's why we can have ethanoic acid and sodium ethanoate. This sodium ethanoate is an highly ionizable salt of ethanoic acid. We can also have a weak base and its salt, for example, aqueous ammonia and ammonium chloride. Aqueous ammonia and ammonium chloride. Another example is when we have the salt of a weak acid and also a weak base. For example, ammonium ethanoate. Ammonium ethanoate is an example of a salt of a weak base and a weak acid. From that, we can have buffer. So let us look at this one after the other. When we have weak acid and it's highly ionizable salt, if you add an acid into this type of buffer solution, let's take it this way. Let's take it this way. We have a weak acid, this, and we have this highly ionizable salt, let's say sodium salt of CH3COO. That is sodium ethanoate. If we have this type of buffer, what will happen is if you add an acid into this environment, what happens with that acid? Immediately you drop an acid there, a very small quantity of an acid. This ethanoate ion, the ethanoate ion, that's okay. Let me clear this so that you can see it properly. The ethanoate ion, which is this CH3COO minus, will briefly mop up the hydrogen ion, the one that is responsible for the acidity of what you have put into that solution. It will immediately mop it up and form a weak acid. So you will definitely have an increase in this weak acid, an increase in the number of moles of this weak acid that you have in the solution. If you add a base into this buffer, what will happen to the base you have added to the buffer? Then the positive ion that you have in the solution will just come and mop up this OH minus that you have put into the solution. And that is what we mean by buffer action. When we have a weak acid and it's highly ionizable salt. So from what I wrote there, added OH, added base will react with, okay, the added OH will react and it will be removed. That OH will be removed by the acid part of what you have in the solution. The acid part of that your buffer. The acid part of the buffer will mop up the OH that you have put into that medium. Okay? I'll modify this. There's something wrong with that sentence. All right. So let us move on. If you have a weak base and it's salt, for example, aqueous ammonia and ammonium chloride. Aqueous ammonia, aqueous ammonia and ammonium chloride. Well, you can also write aqueous ammonia as this, NH3.H2O, depending on how you want to write it. Aqueous ammonia and ammonium chloride. If you have this type of buffer, what happens when you add an acid? If you add an acid, the hydrogen ion will be removed by the aqueous ammonia, and the hydroxide ion will be removed by the ammonium ion. And then there will just be a slight change in the pH, the buffer action, an activity that resists a sharp change in the pH of the solution. If you have a salt of a weak acid and a weak base. For example, ammonium ethanoate. We have mentioned this example before, ammonium ethanoate. What will happen if you have that? The added hydrogen ion will be removed by the ethanoate ion, which is this. And the hydroxide ion will be removed by the ammonium ion. So you will just have, if you put an acid into that medium, the ethanoate ion there will mop up the hydrogen ion you have put into that environment. The number of moles of the acid you have in that solution will increase definitely. So you have more of this weak acid. And if it's a base that you add into this medium, let's take OH as an example. The ammonium part of this ammonium ethanoate will just combine with this, and then you have this aqueous ammonia back. You have the aqueous ammonia back, and this is just a weak base. So the pH of that solution will not be significantly affected. All right. Now let us look at pH of a buffer solution. When we are talking about pH of a buffer solution, two major things are very important, and one of it is the buffer capacity and the pH of that buffer. What do we mean by buffer capacity? That refers to the amount of acid or base, the number of moles of the acid added into that we have. The number of moles of the acid the buffer can neutralize. That is, if you have a buffer solution and you introduce some acid into that buffer solution, how many number of moles of that newly introduced acid or base can the buffer neutralize? That is all we mean by buffer capacity. If you just put slight amount of an acid into a buffer solution and the pH change is very drastic, then the buffer capacity is very low. So buffer capacity is inversely proportional to change in pH. The better the buffer capacity, the smaller should be the change in pH. Or if you have a drastic change in pH, a wide change in pH, it means the buffer capacity is low. So that is all we mean by this equation 13. Okay. Let's take a step further. So we have got to the pH of a buffer solution. The pH of a buffer solution. Okay. Here, I've given you an expression which is pH equals to pKa plus log of the concentration of the anion divided by that of the cation. Look at this equation very well. The log is only appearing once here. We are not having log A minus over log. No, this is wrong. This is wrong. So when you are calculating this, the log is just appearing once. That's just your pKa plus log of the anion concentration over the acid you have put into the solution. The acid. And you can rewrite this equation 14 as what we have below it as pH equals to pKa plus log concentration of salt divided by concentration of acid. These two expressions are referred to as Anderson-Hasselbalch equation. The other thing you have to note in this expression is this plus sign. If you read some textbooks, you will see some minus sign here. I intentionally retained the plus sign, and I retain the plus sign with the manipulation of this ratio of the concentration of the salt to that of the acid. If you reverse this ratio, if you have this concentration of the acid up and the concentration of the salt down, then this sign, which is positive, will change to be minus. But I intentionally retain the positive sign and let us stick to it so that there will not be any confusion in this class. So just take it as pH is equal to, you know how to calculate your pKa now. That is minus log into base 10 of Ka plus log. There is no half. There is no anything here. No half. Don't put any half there. Don't put any half there. This is just pH is equal to pKa plus log into A minus over the concentration of the acid. We'll be applying this equation in the next slide, and we'll be solving this question together. All right. pH of buffer solution. So this is an exercise for you. 0.065 molar of sodium ethanoate is added to 0.02 molar ethanoic acid to prepare a buffer solution. Calculate the pH of the buffer. Assume that there's no change in volume. And also calculate the change in pH if 1 cm cube of 1 molar strong base potassium hydroxide is added to the buffer. How are you going to solve this kind of question? The first thing you have to remember is the formula you will use, and that is equation 14. So the moment you get the correct formula to use, you are getting close to a correct answer. Your pH, the pH of that buffer solution is pKa plus log into the concentration of the salt over the concentration of the acid. Concentration of the acid. So far up to this point, do we have anyone who doesn't understand what we're trying to do? Up to this point of calculating pH. Before I move on, let me see your responses in the chat section. Do you understand what we have done so far up to this point before we move on? Okay. Some of you said they understand, some said they don't understand. All right. Okay. The slide is already available for you on the LMS page. You can go there and download it. This slide is available on the LMS page. Okay. I can see most of your comments. Some of you said, I should repeat it, that you don't understand what we're trying to do. All right. For those of you who understand, maybe if you go over it again, we'll understand it more. Okay. All right. It's okay. I can see your chat. I can see your responses. I can see your responses. Okay. So let's go back to the slide. All right. Let me go over this again. pH of a buffer solution. To determine the pH of a buffer solution, some researchers have already come up with the formula you will use. If you want to go through the first principle, maybe you want to go through how, okay, wait. If you want to go through how an acid or maybe also start dissociating into the anion and the hydrogen ion, or you can just take the final expression we have for the pH. Just try, and by the time you practice using this formula, maybe 1, 2, 3 questions, you'll be getting familiar with this formula. pH is equal to pKa plus log of the concentration of the salt. They can also put it in form of log of the concentration of the anion over the concentration of the acid. Why are we having expression like this? Why do we have expression like this? Just look at what we have. If we have, okay, if we have this, just take this acid, dissociates to give you A minus and H plus. This H plus relates to the hydrogen ion concentration. This A minus looks more or less like the anion, the salt part that you have in the solution. This is the acid you are starting with. Okay? This is the acid you are starting with. So if you have this kind of expression, then you know that where you have this A minus, you are more or less referring, okay, let's say we have CH3, COO, Na, no minus there, Na. If this salt ionizes in solution, you have CH3, COO, negative, plus Na, positive. Right? This is just a part of the buffer solution. Let's say this is the salt of the weak acid. But what is the weak acid? The weak acid precisely is the CH3, COOH. So the concentration of this weak acid, that is what you have here as the acid. For the salt, this salt, the concentration of this salt, CH3COO, the Na can be a spectating agent in this type of reaction. So the concentration of the salt you have, this is what you have as the numerator. And depending on what you're provided with in the question you are given, you can put what you've been given into the expression, I mean this equation 14, and find what you have not been given. For example, in this equation, okay, in this equation, you have been given the concentration of the salt. So you know the concentration of the salt. You have been given the concentration of the acid. So you know the concentration of the acid. There are two major things you don't know here. One of them is pKa, and the other one is pH. How will you know the pKa? You are dealing with acetic acid, or let me call it ethanoic acid. CH3COH is a weak acid. So you can refer to what we call table 1 that I gave you some time ago. You just take some slides back. I gave you table 1 where I put the dissociation constant for acids and also for bases. Just refer to this table. Just refer to this table. For acetic acid is the same thing as ethanoic acid. It's the same thing as ethanoic acid. So just look at it. Okay, let me reduce this screen so that you can see it very well. The Ka is 1.8 times 10 raised to power minus 5. 1.8 times 10 raised to power minus 5. That is the Ka value. You can use this Ka value to calculate the pKa. You already know the equation to use. You already know the expression to use. So let us go back to where we were. 1.8 times 10 raised to power minus 5. Okay. All right. So your Ka is 1.8 times 10 raised to power minus 5. How can you calculate pKa from here? Just try it. Minus log to base 10 of 1.8 times 10 raised to power minus 5. I'm waiting for you. For those who have their calculators there, very fast ones, just punch your calculators and tell me what you have if you solve this expression. What did you get? What did you get? 4.74, 4.75, 5.26. Okay, you got so many things. 4.74, 5.26. Okay. All right. Remember, I told you that you have to be very familiar with your calculator. Just ensure that your calculator is working very properly. What you have been asked to calculate is pKa, not the pH yet. pKa, not the pH yet. Your answer is 20. Oh, the person who got 20, that is a very big answer. It's not supposed to be 20. You don't actually need a table in your exam. All the values you will need, either for your test or for your exam, all the values you need will be provided inside that, under that question. You don't need to cram all this. Every value you need will be provided, either in the test or in the exam. Every constant value you need will be provided. Okay, the correct answer is 4.74. So if you have got 4.74, you are correct. If you got 4.7447 or something, you're also close. You're on the way. Yes, you're correct. If you got 4.75, maybe you did a lot of approximations. Maybe. But if you get 4.74, you're okay. It's very okay to have that. But 20 is not the correct answer. 5.26 is not the correct answer. 4.71 is far away. Maybe we did a lot of approximation. Okay, so let us go back to that slide and see. All right. You have already helped us solve this. So our pKa is equal to 4.74. Some of you, I've been saying it that when you want to solve equations like this, just be very familiar with your calculator. Be very, very familiar with your calculator. If you just find maybe minus log 1.8 and you did not find it together with this times 10 to the minus 5, you will get a different answer. If you just calculate, maybe instead of using plus or something, you put a negative sign there, you'll get another answer. So be familiar with your calculator. If you don't trust your calculator, you can buy another one or maybe borrow another one. Cross-check them. Use the calculator on your phone. Cross-check with the calculator you have bought to see if the values are the same. And that will give you more confidence in the test or in the exam. So our pKa is, okay, let us use 4.74 for our pKa. Then the value for our pH is we are getting close to that. We have 4.74 plus log into, we'll put the salt at the top. What is the concentration of the salt? That is 0.065 divided by the concentration of the acid, which is 0.02. Press your calculator very well. What will be your final answer? What will be your final answer? Just press it. I want to see what your answers are. Okay? For the pH of the buffer, what is your answer? 5.25, 5.25, 5.7. Okay. I'm seeing so many things. Five point two five, 5.25. Okay, most of you got 5.25. 5.75. Okay. 5.257. All right. All right. Just keep trying and keep sending in your responses. The more you try, the more you solve this. Don't be afraid of this question. Just try and solve it. The more you attempt this question, the more the confidence you have in attempting further questions. So whether you get it or not, just try something from your hand. All right. I can see more responses coming in. Those of you raising your hands, maybe you should get tired of raising hands or entertain some questions, maybe one or two, before we leave the class today. All right. Okay. All right. If you actually got 5.25 for the pH, you are correct. If you got 5.25 for the pH, you are correct. 5.25, 5.25 something, around that range. Just ensure that you are within the correct range. 5.25, 5.25, 253, 25. Those range, just be within that accurate range. And ensure that you don't introduce a lot of approximations into your work so that you can get correct answers. Then, this is the next question for you. Calculate the change in pH. If 1 cm cube of 1 molar KOH is added to the buffer, if you add 1 cm cube of 1 molar strong base, what will be the change in the pH? So when you introduce an acid, maybe a strong acid or a strong base into a buffer solution, the pH changes, but not significantly. So let us try and see if it's actually significant or not significant. You have a new pH will be established when you introduce an acid or a base into the medium. A new pH will be established. Since you are introducing a base into this, the concentration of the base part or the salt part will increase, and the concentration of the acid part will reduce, because part of this base will be neutralized by part of the acid that you have in the solution. So it will be neutralized by part of this ethanoic acid. So the number of moles of this ethanoic acid will reduce because you're introducing a base into that buffer. And the concentration of the salt or maybe the base that you have in the medium or the anion, the number of moles will increase. So just remember what I've said very well. 1 cm cube of 1 molar KOH. What is the meaning of this? Convert this 1 cm cube into dm cube. 1000 cm cube is equivalent to 1 dm cube, right? If you remember those things you did in secondary school, 1000 cm cube is equivalent to 1 dm cube. And if you have 1 cm cube, 1 cm cube will be 10 raised to power minus 3 dm cubed. 1 cm cube will be 10 to the power minus 3 dm cubed. So that is the volume you have, okay? If you want to get the number of moles with this, what would that be? You multiply 1.7, this, let me clear the screen so that you can see it. You multiply this 10 to the power minus 3 dm cube, that is the same thing as 1 cm cube you have, by this 1 mole per dm cubed. What would this give you? You have 10 to the power minus 3 mole. 10 to the power minus 3 mole. If you introduce this 1 cm cube into, remember you have 1 liter solution, 1 liter solution, because this 0.02 mole per dm cube, that is mole per dm cube. Dm cube is the same thing as 1 liter. It's the same thing as 1 liter. This suggests that the volume you are dealing with will have changed. The volume that you're working with, the volume of the solution will have changed, will have increased by 1 cm cube. So instead of having 1000 cm cube, you will have 1001 C. Let me clean the screen. You will have 1001 cm cubed of solution. So the volume will have been modified, though not significantly. The volume will have changed. Okay. If you have followed it up to this point, let me see your hands. I mean, just signify. If you have followed this up to this point, signify before we move on. Okay, you said I should come again, I should explain again. All right, I will try as much as possible to explain again. Okay. All right. You said it's not clear. Okay. If you said it's not clear, we'll go over it again. All right. It's okay. I can see your responses. It's all right. I can see your responses. Let's go over it one more time. This, I'm trying to sketch for you now. Say this is the buffer solution. The total volume we have here is 1000. I'm converting 1 dm cube to cm cube. We have 1000 cm cube originally. Then to introduce 1 cm cube, you just take maybe a very small measuring cylinder, and you put just 1 cm cube. You add 1 cm cube into original 1000 cm cube you have. What will be the new volume? The new volume will have changed to 1001 cm cubed. 1001 cm cubed. Okay. I hope you understand just what I've said. But this change in volume is not very significant. You can also take it into consideration, but it's not very, very significant. All right. Then you can calculate the number of moles of this your base you have introduced. You know, we already have the concentration, which is 1 molar. Calculate the number of moles. You know how to calculate from concentration. Concentration equals to number of moles divided by volume. Concentration equals to number of moles divided by volume. Okay? And the number of moles will be concentration times volume. What is the concentration? 1 molar, right? Times, what is now the volume? What is the volume? The volume has now increased. Okay? Maybe you convert for you to be able to solve this properly. Ensure that you are managing your signs. I mean, you're managing your units very well. If you want to convert the DM cube, if you want to convert the DM cube to CM cube, ensure you retain CM cube on both sides for the concentration and the volume. And if you want to use DM cube, ensure that you retain DM cube for both sides. I hope you understand what I'm trying to say. Okay. All right, let me get your response before I move on. Oh, it's already 6 o'clock. All right. I think it's already 6 o'clock. It's already 6 o'clock. Okay. So this is what we're going to do. This is what we're going to do. Just try from your hand. I will flash the answer now. Just look at the answer and we'll continue from here on Monday, God willing. We'll continue on Monday from where we have stopped today so that we'll look at this question together. I will give you a short test also that you work with. You will look at how we do it. Okay. No, don't let us extend it till 6:30. We'll continue this class next week by God's grace. If you have questions, just send in your questions under the chat section. Then we can look at how we will be able to solve those questions together. I will be able to go through your chats. And this slide, today's class will be available on your LMS page. For those who are also following it on YouTube, you can just follow it very properly. Okay, so don't worry. We'll continue next week. Let me wish you a very great time. Just try and attend to the question. I'll flash the screen again. You can take down the question. Okay, you can take down the question. We can screenshot it any way you want to take it down, but it's already available for you on the LMS page. Don't worry, Adeniji. Okay. All right. Let me wish you a very nice weekend.